Okay, so welcome everyone to the Simon's Quantum Colloquium. So today it's a real pleasure to have Dolev Bluvstein here with us from Harvard. Dolev is actually a PhD student in Misha Lukin's group. He's also the first author on the recent paper on neutral atom quantum computing, which has been making waves. And I think it would be no exaggeration to say it's probably the most dramatic development in experimental quantum computing in the last few years. And I understand that Dolev played a big role in the experiment, and we're really looking forward to hearing your talk about it. Okay, Dolev.
Thank you so much, Umesh. Okay, let me share my PowerPoint. Okay. Great. Okay, and I'm very happy to receive questions during the talk. Okay, so should I get started?
Yes, please.
Okay, fantastic. Yes, so I am indeed going to tell you about our recent experiments using this machine we've developed at Harvard, where we're now using this for doing quantum computation with logical qubits. And starting off, more broadly, there's many different frontiers of experimental quantum information that we find quite interesting. And in the past, decade or so, there was really remarkable work done in the field studying, in particular, small-scale computations with physical qubits, and starting to really play with, physical qubits and quantum algorithms in the lab and see what do quantum algorithms look like. And recently, there's been kind of a lot of, now that we can control these systems quite well, we can start to put all these different interacting quantum particles together and, for example, study new physics. And this is this kind of age of quantum discovery where we can use these tools really as scientific instruments and try to learn new things about quantum mechanics. And the other aspect that has really started to emerge is that of doing quantum error correction in the lab. And here, what we've been able to start doing is, use physical qubits and our control over them in order to entangle them into conglomerate qubits that we call logical qubits that are protected from errors. And in the past few years, there's been really remarkable kind of really fast breakthroughs from various different approaches and being able to kind of make the first 1, 2, or maybe 3 logical qubits and operations. And today's talk will be focused on quantum error correction. And this topic is actually, of central importance. In particular, in our large quest to be able to build a large-scale quantum computer, finding decoherence is really the central challenge, at least from an experimental perspective. And at least to date, quantum error correction is the only known realistic route that we have in order to be able to suppress the gate errors from what we have with our physical qubits at the scale of, for example, 10 to the minus 3 to the algorithmically relevant ones of, say 10 to the minus 10. And actually, in fact, before quantum error correction was invented, I was not around at the time, but people thought quantum computing would, be even, fundamentally impossible before this kind of theoretical breakthrough. And it is quite remarkable, even from a, fundamental physics perspective, that quantum error correction is possible. Classical error correction works in a very simple way. We can, make copies of a bit, for example, that we care about, a bit 0, and then copy it 3 times. And now if any of the bits fails, we can detect that it failed and do majority voting. Quantum error correction, however, has these, several conceptual challenges. One is that we can't copy quantum information. There's this infamous no cloning theorem. And another is how can we even check, for errors without collapsing the state? And so again, it's quite remarkable, this theoretical breakthrough of quantum error correction is even, physically possible to begin with. And the key idea, at least the way that we think about it, is that what we're going to use is entanglement in order to take a single qubit of information that we care about, our logical qubit, and we're going to use entanglement to delocalize it across many individual physical qubits. So now if the environment comes in and tries to measure any given physical qubit, it actually will learn nothing about the underlying state. And it becomes, hard for us to accidentally manipulate this logical qubit degree of freedom now that it's delocalized. And it turns out that actually, by measuring products of qubit states, the stabilizers, we can actually detect errors while preserving this encoded quantum information. And a classic example of this is the, this Torah code invented in 97 by Kitaev. And this Torah code is given by a lattice of qubits here on a torus with periodic boundary conditions. And the error-free state of this quantum error correcting code is the case where all X and Z products, all of these stabilizers, these X and Z operators here, these four-body products, are equal to +1. And then in that state, we can actually just read off the state of the logical qubit by looking at the X and Z strings that run vertically and horizontally across the lattice. And the way that this works here in practice is if we have something like a physical qubit error, like an X error on this qubit here, it'll anti-commute with two of our Z stabilizers. And we'll see that there was this error locally without, again, collapsing the physical qubit states. And as we increase the size of our code, or we increase our code distance D, we get more opportunities for errors because we have a larger system, but we also get more checks. We get more opportunities to kind of locally infer where these errors may have happened, and we get a kind of threshold behavior where the logical error probability can, in principle, be reduced exponentially as you increase the size or the code distance. What you need is to be below this kind of characteristic threshold, which in state-of-the-art error correcting codes like the surface code or toric code is kind of at the scale of roughly 1% for your physical qubit fidelities. And what this now gives us is a relatively realistic route, or quite a realistic route, in order to be able to get to these extremely small errors of 10 to the minus 10 that we have in mind. So it was really this theoretical breakthrough of quantum error correction that showed that physically this task of building a quantum computer is even possible. And although we've learned so much doing algorithms with physical qubits in the lab, it is understood that eventually we will need to switch to regularly performing our algorithms with logical qubits, because this is what we will need to do in order to be able to build really large-scale quantum devices. But of course, there are challenges, and quantum error correction broadly is actually quite challenging. And if you look in the literature of what are the kind of optimistic estimates of what we might need for doing large-scale problems, we're thinking about things of like the scale of millions of physical qubits, creating logical qubits that have errors on the scale of 10 to the minus 10, and doing complex algorithms between that. And something that greatly compounds this challenge is that of efficient classical control. So although with our classical computers, we've gotten really good at taking something at the scale of 1,000 wires in order to control billions of bits. With the quantum devices that we've built to date, it often works in this way that we have several wires per qubit, and each new qubit that you add, you have to add more wires. And it kind of this so-called wire problem poses a significant challenge to doing this large scale control over these millions of physical qubits. And another kind of really important challenge here is that once our logical qubit becomes delocalized, it also becomes hard to operate on. And for this reason, this large overheads and the complexity of actually doing operations have focused, existing studies to the scale of 1 or 2 or 3 logical qubits and gates. So I'll tell you now about our approach to this problem, which is using what we call these reconfigurable atom arrays, where there's many kind of pioneering developments in the tweezer community over the kind of the past years. So what this looks like is we have neutral atoms, neutral rubidium atoms, that are trapped inside of optical tweezers, and these can be, for example, placed in multiple zones of our processor. We store information in this hyperfine qubit state. This has coherence times on the scale of seconds in our system. And we generate entanglement by quickly exciting atoms into this Rydberg state. They quickly entangle. We bring them back down to this hyperfine qubit state. And then because the coherence is so long, we can actually move these qubits around in the middle of the quantum computation without losing coherence. And the two really unique opportunities that we're going to get from this reconfigurable atom array approach is one is non-local connectivity, which turns out for error correction is exceptionally useful. And two is it's going to give us the ability to do parallel and efficient classical control, which I'll kind of try to explain why it's so central for doing quantum error correction. And please interrupt me with questions whenever. So okay, and I also want to just kind of highlight that what we're doing here is dramatically building off of the kind of amazing progress that has come before. So in particular, trapped ions have had decades long vision of doing a shuttling based architecture and kind of understanding the benefits of that. It's actually from the superconducting qubit community that we learned so much about the importance of doing parallel and efficient classical control, and learned about this wire problem. And really, there's been decades of cold atom research, which are kind of the original pioneers of doing parallel and efficient control of many identical atoms, that we're also kind of leveraging a lot of the insights from. And we're kind of leveraging kind of all these various communities in our approach. So okay, so first in this talk, I'll first kind of give you a quick overview in terms of how do we program quantum circuits with neutral atoms, and then I'll dive into our recent results doing logical processing. Again, please ask questions whenever. So okay, this is how all of our experiments start. This is not particularly remarkable to our lab. It starts with a neutral atom is trapped inside of this magneto-optical trap. We have roughly 10 million atoms in this millimeter-sized region of space. And again, this is not remarkable by any means in our lab. It's standard atomic physics. But what this picture really shows you and makes very clear is that cold and identical neutral atom qubits are essentially unlimited. Number of atoms is never really a problem. The problem is always how to control them. They're already right there, and now the kind of task of building a quantum computer out of them is figuring out how to control them all. And that is baked into how we do our experiment from kind of the very first layer, where we have 1,000 plus neutral atoms that we trap in these 2D tweezer arrays. What this looks like is we make a MOT inside of our vacuum chamber, and then we trap these atoms with these individual optical tweezers, where each tweezer traps one atom. And the way that we generate these thousands of tweezers here is we just take one laser beam, we imprint it on a spatial light modulator, which splits this one laser beam into many individual laser beams, and we control the spatial light modulator just like we're controlling essentially a computer monitor, and then it gets focused inside of our vacuum chamber. Another really important someone ask a question? Okay. Another really important optical tool is the acousto-optic deflectors. This allows us to move the qubits dynamically in the middle of the circuit, and allows us to, for example, here do parallel rearrangement of these qubits into defect-free grids. Here, a 400 atom defect-free grid. Originally, the loading is stochastic. But what's really important about this optical tool, and the kind of really key takeaway to have, is just these two small boxes, and they have one voltage wire for X, one voltage wire for Y, and then using frequency multiplexing, this allows you to create large dynamically programmable grids of light that you can quickly move around by just changing these two voltage waveforms. It's something that's really central to being able to do parallel control, and is used pervasively throughout the neutral atom community. And we can, make many different shapes, not only, square grids, we can also, make Kagome lattices, or we can make, Mario videos for fun. And kind of shows you that, what we have, really well developed in this neutral atom community is how to position atoms in really efficient ways. So that's kind of how we lay out the processor to do, entanglement and also quantum physics. We use this Rydberg state, where the orbital ground state of the atom is quite small, but then what we can do is zap the atom with a very precisely tuned laser frequency. And now the atom will go not to principal quantum number of like 1, 2, 3, or 4, but to n equals 50 or 70 in a coherent way, and the atom gets significantly larger. A really important consequence of this is that now if we have two atoms that are next to each other, and we simultaneously try to excite them to the Rydberg state, there's actually a very strong van der Waals interaction between both atoms being in the Rydberg state. And they actually, because of this very large energy penalty, which is at the scale of gigahertz, at the scale that we put the atoms apart, this makes it such that adjacent atoms cannot be simultaneously excited. The interaction strength is too large. And this gives this Rydberg blockade mechanism, where now if we put two atoms next to each other in the ground state, we simultaneously try to excite them into the Rydberg state. They'll both try to go, and they'll compete because they won't be able to decide who gets to go, and they'll go into an entangled superposition of Rydberg ground plus ground Rydberg, and that generates entanglement in a way which is independent of the interaction strength between the atoms, because it's essentially infinite. So we've used this Rydberg blockade mechanism to do a variety of analog or kind of Hamiltonian evolution simulations in the past few years, where what this looks like is we have, for example, a Kagome lattice. We turn on a global laser. There's dynamics under this Rydberg blockade mechanism. And then, for example, a quantum spin liquid may emerge. We can also study things such as phase transitions, non-equilibrium dynamics, combinatorial optimization. And it's just using, these simple tools of placing the atoms and then just global parallel control of exciting them to the Rydberg state. But now, to do quantum error correction and kind of other various investigations, we want to be able to also have digital tools. And what this looks like is now we have a quantum circuit that's decomposed into gates, single qubit and two qubit fundamental building blocks. And we want to be able to realize, these controllable operations in order to be able to do universal quantum computation, right? So there's many more degrees of freedom in this system, but we really still want to be able to figure out how to do efficient classical control. Something that was a really important breakthrough here a few years ago is the development of this Levine-Pichler two-qubit gate. And what this looks like here is, again, our qubit state is defined by this hyperfine qubit that stores information for long times. It has this microwave separation. And to do an entangling gate, what we want to do for the CZ gate is just map all the computational basis states back to themselves, but the state 1,1 should come back with a different phase. And it turns out that you can do this with just a global drive of the Rydberg laser. The atoms, go from 1 to R, and then they come back down. And then in particular, just due to this Rydberg blockade mechanism, If both qubits are in state 1, this entangled coupling to this, entangled superposition state generates a different accumulated phase for the state 1, 1. And then just using these global laser pulses, we're able to generate a different phase for 1, 1. And, in this simple way, do an entangling gate. So the kind of really key takeaways here on a practical level for this Levine-Pichler gate is that it's using global pulses and it's using blockade. And what this blockade mechanism means is that if two atoms are next to each other, they do an entangling gate. And if they're not, then they don't. And this allows now for us to start programming our quantum circuits by using the positions of atoms. And this is the first quantum circuit we ever ran doing a 12-atom 1D cluster state, which looks like we put all of our qubits in plus and then do CZ gates on the links between the qubits. And in particular, what we do is we put atoms in pairs. We pulse our one global pulse of this excitation rate, this Rydberg excitation laser. This entangles atoms on these adjacent links. Then we move half the atoms in parallel. We do this by changing one voltage waveform that, again, controls all these atoms with frequency multiplexing. Pulse the second laser again. And just in these two parallel steps, we make this 1D cluster state that we can probe here by looking at the cluster state stabilizers that take the form of ZXZ. And it shows successful creation of the state. So again, really the very central takeaway in terms of how do we program quantum circuits with this reconfigurable atom array approach is that this position defines the gate through blockade. And we have, in the community developed really efficient control over controlling, these qubit positions. And now this maps onto doing efficient control over complex quantum circuits. So this was the kind of first circuits that we had done. These cluster state stabilizers here show a successful creation of the state. The fidelity here was limited. These stabilizers should be 1. The fidelity here is limited by our old 2-qubit gate fidelity of roughly 97.5%. And we've done a variety of kind of upgrades in the past year in pursuing, universal and high fidelity digital circuits. One of them is that we have these 99.5% 2-qubit gates on 60 qubits in parallel that we benchmarked. Here we're using a higher power laser and also changing our gate technique. There's also been really nice work from the Thompson and Endress groups, and I think this gate fidelity is something that's going to continue improving in the community. So that was one kind of important upgrade. Another is that we have fully programmable, but also parallel single qubit gates. So we actually use another AOD, and we send our single qubit light that controls this hyperfine transition through this other AOD. And what this allows us to do is, for example, an arbitrary rotation on any qubit if we want to. But importantly, what it also allows us to do is use frequency multiplexing to make a rectangular grid. And for example, if we want to address half of our qubits that live on a rectangular grid, and we want to just do a Hadamard on half of the qubits, we can do that in one parallel step by just illuminating this one rectangular grid and sending the same single qubit addressing instruction to all of these qubits. And then another really important aspect is that of doing mid-circuit readout and feed-forward. There's many different approaches people have now demonstrated for doing mid-circuit readout and feed-forward, and all of them seem to work just fine. Our approach is we move the qubits away in the middle of the computation to a separate zone. We call this the readout zone. We scatter photons off of these atoms there without perturbing the qubits that we care about. We see that it doesn't decohere them, and we can get high fidelity state discrimination. So this is our approach to doing mid-circuit readout and feed-forward. Oh, I see a hand.
Yeah, hi. I thought I'd give you a break by asking something, but maybe this is something for the end. But when you've said atoms up till now, it's always rubidium, true?
Yes. Yeah, everything I've talked about is rubidium.
Do you have a view that someday it should be something else because of details that you're really not talking about here?
Oh, so this will be, I think, a perfect question for the panel because Jeff is also going to be on the panel. I mean, everything I will show you today is fully compatible with any atom you choose. I mean, in my belief, we're probably exploring the right atoms at the moment. Not just rubidium. I think there's many other kind of, interesting atoms that people are exploring, including ytterbium, cesium, strontium, etc. And yeah, I think I mean, in principle, you could do everything I'm showing today with ytterbium as well, or strontium or cesium, etc. And I think we are, maybe this is more of a discussion for the end, but this is such a long journey that now is absolutely the right time to be exploring these different things. I don't think it's the right time to commit to one particular atom. Yeah. Okay, thanks. Someone else, there's another raised hand. Oh, okay. All right. Okay, I'm going to keep going. Okay, so that is kind of, a high-level overview of how we program quantum circuits with atoms. And now I'll tell you some more about how we're exploring quantum error correction. So this was one of the first, in our first work doing quantum circuits with this reconfigurable atom array. This was, one of the circuits we made, which is this toric code on a torus here. And what this looks like is we have 16 data qubits in our torus that are fixed in these SLM grids. And then we have these 8 ancilla atoms that are kind of rocketing around the system. And every time we put atoms into new pairs, we pulse this global laser, and this entangles these atoms in this just parallel step. And we can also move the atoms all the way around to make the periodic boundaries for this torus. And the thing I cannot emphasize enough is that the circuit is being programmed here just by a specific SLM profile and this AOD waveform. And this gives us here this parallel control over many physical qubits, and here a logical qubit, in order to just use using order of one classical controls. And when we were doing this, what kind of became apparent is that a really natural direction of these tools is focusing on doing logical quantum computation from the lens of thinking about how do we do efficient single logical qubit control as opposed to single physical qubit control. And this is something that quite naturally multiplexes with optics. So for example, if you imagine having an array of surface code logical qubits, and you want to do, for example, like a single qubit gate, then we learned from Peter Shor and others that we can do this single qubit gate in this transversal fashion, where we don't have to do a unique operation on each individual physical qubit in the block. We can essentially just take one big beam and send the same exact instruction to all of the physical qubits that make up the surface code logical qubit. But importantly, we can also do this for two qubit gates. So if we want to realize a transversal entangling gate between two logical qubits, all we have to do is just pick up these two grids, interlace them, pulse our one global pulse of the entangling laser, and then in this way do pairwise CNOTs between each of the individual physical qubit twins of the block. And in this simple way, we can do in a single parallel step this transversal CNOT. And this now allows us to start exploring efficient and parallel computation with logical qubits. And I really want to park on this transversal CNOT for just a little bit longer because it's central to what I'll talk about for the rest of the presentation. So earlier I mentioned how by being delocalized, our logical qubit degree of freedom becomes hard for us to accidentally manipulate. But the challenge is it also becomes hard to intentionally manipulate. For example, if we have two logical qubits and we kind of delocalize them, and now we're trying to interact them, but we have to do this with 2D connectivity on a chip, then now it's pretty hard to get these two delocalized wave functions to interact. But what we can do is we can actually just take these two delocalized wave functions, put them right on top of each other, and then just do a pairwise CNOT between each individual twin of the blocks. And there's a single parallel step entangle these two logical degrees of freedom. There's many benefits of this approach. One is that it's inherently fault tolerant. Fault tolerance means that errors can't spread within the code block, which is really important for doing successful quantum error correction. And this means that D rounds of correction are not required between each gate, unlike lattice-based approaches. It also gives us long range and direct connection between logical qubits, which can actually have quite significant savings for doing large-scale algorithms. And again, from an experimental perspective, I guess I've said it so many times at this point, but all physical qubits receive the exact same instruction to do this logical operation. We act on it like it's one big atom. Yes.
There's a question here. Can you hear me?
Yeah, I do. Yeah.
This is really great, but in a physical system, the light intensity may not be the same across the whole array. There are always things. And since you want to do this in high fidelity, those variations in light intensity will degrade the gate. So what? Yeah,
so it's really important to make sure the beam is homogeneous, for sure. Yeah, and yeah, it's true. All the atoms are identical. The light is not always identical in all regions. Not all regions of space are identical. But I mean, we're relatively good at homogenizing these laser beams. Engineering that to very high precision will be more important in the future. But I didn't show this. But for example, with our 60 qubit gates, we have other than statistical variation, our 60 qubits doing 2 qubit gates, we don't see any variation across the array. That requires us to be, again, patient with homogenizing the laser beam. But this is something I think can be extended for sure.
So no variation giving what kind of error?
Oh, well, I mean, it's like 99.5%, and then, maybe like 0.03%, like variation. I mean, because consistent with statistical error.
Okay, thank you.
Yeah. Yeah. It's also very clear. I mean, we look at the intensity on the atoms, and if it's inhomogeneous, then there will be variation in the gate fidelity. If it's homogeneous, which we again we use a spatial light modulator to make this Rydberg beam, and we have control over the beam, so we can homogenize it. Yeah. Okay, great. Thank you so much for the question. Okay, so using these principles, we're building here what is our first generation logical processor. We're also leveraging the zoned architecture here. And again, the key focus of our approach is doing parallel control of many logical qubits with only a few wires. So we're utilizing these transversal gates that we discussed, which are inherently fault tolerant. We have a storage zone where qubits can be stored idly for long times, where they're safe from errors due to the long coherence times in the system. We have an entangling zone where we can pick up two logical qubits, move them in, and entangle them with a single parallel step, and this readout zone where we move qubits away and read them out without disturbing these active qubits. And as mentioned, this long-range connectivity gives many opportunities, not only for transversal gates, but also for studying exotic codes. Okay, so that's the kind of processor we're looking at. And now it's kind of a first example. I'll tell you about how we're going to do a transversal CNOT between two surface codes. And so what this looks like, and the way we're going to probe it is by probing Bell states, just like we do with our physical qubits. We're going to prepare one of our surface codes in state plus and the other in state 0. The way we do this is we initialize these two sets of data qubits. And then on one, we measure the Z stabilizers, and on the other, we measure the X stabilizers. We use this ancillas to measure the stabilizers. We move the ancillas away. And then we do this, transversal CNOT with this interlacing procedure. So a really key and important property of quantum error correction is that operations should improve as you increase the size of the code. There was this, really beautiful work done by the Google team recently showing that, you can improve the idling operation or the coherence time of a qubit by increasing the size from distance 3 to distance 5. And there's also this really nice work entangling to distance 2 surface codes in ion systems using lattice surgery. Here we're expanding, from distance 3 to distance 5 to distance 7, probing this transversal CNOT as we increase the size of the code. An important caveat is that here the state preparation is not fault tolerant, but it actually turns out that it's okay for probing the behavior of the transversal CNOT. And I'm very happy to answer any questions about that. But but to probe this transversal CNOT here, we're going to look at these these Bell state stabilizers, these logical Bell state stabilizers in the XX and ZZ basis. And what we see is that this logical Bell pair error reduces as we increase the size of the code. And this means for us that we're improving how well we can entangle two logical qubits as we increase the code distance. Important comment I want to make here is that the effect. So this shows we're below some effective threshold of our entire circuit. This effective threshold is a bit higher here because we have these nearby time boundaries in our decoding. And something that will be a really important aspect of future work is not just doing a single transversal CNOT and seeing if we can improve it with code distance, but actually trying to do more transversal CNOTs, which will require doing transversal CNOTs interspersed with rounds of error correction to continuously remove entropy. And that's an important thing that we're trying to work on. Another important comment is that once we're doing these algorithms with logical qubits, it does change a lot the kind of way we think about certain problems, such as, for example, the decoding or this inference process of where the errors may have happened. And in particular, we're using this technique here that we call correlated decoding, which improves the fidelity of our logical circuits. In particular, in this circuit, it makes us much more robust to the non-fault tolerant errors in the state preparation. And it's a simple observation, which is that when we do these gates between logical qubits, if we have, for example, a physical error on one of the blocks, then it'll propagate into a correlated error between the two blocks, even though it's still fault tolerant. And we can account for this by adding edges and hyperedges to the decoding graph that does the joint decoding of these two logical qubits. And this is being led by a theorist in our group, Maddie. And we also kind of are, exploring this theoretically. We can see that, for example, this allows us theoretically to reduce how many rounds of error correction we need to do per CNOT from, D to order 1. It also, works primarily for Cliffords, but it also it's still useful, but for doing non-Cliffords. But the kind of what I want to comment on here in terms of this correlated decoding is a really key observation we've had doing these logical algorithms in the lab is that it becomes, quite prudent to start considering, not individual logical qubits, but considering quantum algorithms as a whole. At the end of the day, especially if it's a Clifford circuit, it's just one big stabilizer state anyway. And so it doesn't really make sense to, think about logical qubits independently. It really makes sense to think about them together. It's really related also to the space-time decoding concept people have been working on. So I'm going to take a quick pause. Okay, fantastic. So that's one way in which we're using this transversal CNOT and exploring it here. Another way is we made two distance 3 color codes or Steen codes, and we're going to probe their state preparation, doing kind of almost like an ion style experiment. We do a non-fault tolerant state preparation of both of these two Steen code logical qubits. And then we do this transversal CNOT by moving these guys on top of each other. And then we use this bottom ancilla logical qubit. So we have an ancilla logical qubit here that's acting as a flag. And then by post-selecting on this flag, not having shown any errors, this becomes a fault-tolerant initialization of the other logical qubit. And if we don't do this fault-tolerant state preparation, then the state fidelity is quite bad. It's like 98%, and it's worse than our physical qubit. But if we use this flag here, again, very similar to kind of ion implementations, then we get this break even with getting 99.9% spam, which is quite a lot better than our physical qubit. initialization fidelity. So what we're doing here, again, some bullet points, is that we're using error correction in order to improve the fidelity of our state initialization, and we're heavily relying on this transport-based C0 being effective for logical operations. But again, I can't emphasize this parallelism enough. We never really do things on individual. I mean, we can do things on individual physical qubits. Sorry. But as much as possible, we do things in parallel, both on the physical qubit level and on the logical qubit level. So this data here is, averaged over, 10 total logical qubits or 5 logical pairs. And now that we've prepared all these logical qubits, we can start to use them for algorithms. So if we have, for example, these 10 logical qubits, there's many different things that we can do with them. Here, what we chose to do is make a GHZ state as kind of, a simple probing of our system. And what we do is we use, the bottom 5 logical qubits as ancillas. We do this kind of Steen error correction step where we, again, fault tolerantly prepare the other logical qubits, then we move them to storage where they're safe from errors. And then we make a GHZ state in 4 out of the 5 remaining qubits. We chose 4 just because it was easier for doing tomography. And then we probe the fidelity of our GHZ state. One of the reasons we chose color codes here in particular is because they have, the whole transversal Clifford group. And this is actually quite convenient for, for example, doing some things that we like to do with our physical qubits, like tomography. And so we measure the qubits in all of these 81 possible logical bases. And then we see the GHZ state fidelity where fault tolerant, using this fault tolerant initialization, error detection fault tolerant is also doing post selection on the stabilizers of the computation logical qubits as an error detection approach, which improves the fidelity, but at the cost of measurement time, of course. And it's shows this genuine multi-part entanglement. And again, we can start to do things that we know and love with our physical qubits, like doing tomography, but start to do them with logical qubits. And here do tomography of this logical GHZ state and kind of explore the various different nuances and intricacies of doing logical quantum computation as we kind of start to explore this early fault tolerant regime. Take a quick pause. Okay. Here's a movie of what exactly this logical circuit looks like. So we have these 10 logical blocks that we're going to encode into these Steen codes. And then in this first 1, 2, 3 steps, we encode non-fault tolerantly. Then we use the 5 top logical qubits as ancillas, do a transversal C0 in parallel, drop them off in the storage zone. We pick up these 2 logical blocks in here and start to kind of just slide them around. And, in this way, do these kind of parallel transversal C0s. I wish I would have included a screenshot from Peter Shor's transversal C0 original paper, but yeah, we're here doing pairwise operations on all of the qubits that make up the block, and that's how we're doing this logical processing here. So here we're using that for studying GHZ states. But you can see that this approach quite directly scales, where now we're going to make 40 of these distance 3 color codes, where again people have previously made 2 of these. And working in this with 280 physical qubits, and we're leveraging insights from, for example, classical computer architectures, where we're going to access storage, operate on qubits, drop them back off in storage, pick up new qubits, operate on these identical atoms or identical rubidium atoms in the exact same region of space where the laser intensity is exactly the same, and do more operations on them here. Again, really inspired by classical architectures where you can take information from RAM, process on it, put it back in storage, and so on, with the cost of some serializing overhead. But you can see the kind of perspectives that we're approaching this from, really kind of thinking about efficient architecture level control. That is kind of some leveraging of our storage zone. Here, I'll tell you a little bit more about our mid-circuit readout. So as just a simple test case of this, what we're doing is we do a kind of entanglement teleportation experiment where we make a GHZ state out of 3 logical qubits. We measure the middle one, and then by doing classically conditioned S gates between these outer 2 logical qubits, we can entangle them even though they didn't interact. And so we pick up this middle logical qubit, do a transversal C0 between these 2, and then move it out to our readout zone, scatter photons off of it, decode the state live, and then do classically conditioned S gates. And in this way, we can project into this Bell state. If we don't do the feed forward, of course, the parities disappear. If we do the feed forward, then we recover a Bell state fidelity of roughly 78%, limited just by the underlying 3-qubit GHZ state, which is the same within error bars of if we just post-selected on the middle logical qubit being in the state plus. So our mid-circuit readout and feed forward works at high fidelity. And the whole time scale here is 800 microseconds. I can discuss time scales more if people are interested. So, okay. I'm going to keep going. Please interrupt me with questions. I'm not monitoring the Q&A, but I'm assuming that someone will interrupt me if I should answer something. So that, was kind of characterizing various aspects of our approach. But, one of the things we've been very inspired by once we've been starting to build these logical processors in the lab is, we have, these quantum error correcting codes and algorithms and our native hardware capabilities. And we're really inspired about this kind of, process of doing co-design between all of them and thinking about how to kind of leverage them for each other. And our view here is that in that, this, as we're entering this era of doing early fault tolerant quantum computation, this kind of co-design approach of kind of cleverly picking the algorithm and cleverly picking the logical qubit encoding can, take us quite a long way in terms of being able to solve new types of problems. So, one of the big challenges with error-corrected quantum computation that I, completely swept under the rug is being able to do universal gate sets. So in particular, quantum error-correcting codes only have a discrete gate set available, and for very, fundamental reasons. And the 2D codes that we talked about so far, like the surface code and the color code, can only do the Cliffords easily, like H, S, and C naught, but they can't easily do a non-Cliffords, which, like T or CCZ, that we need to complete our universal gate set. But it's actually even worse than that if we're kind of exploring small-scale quantum algorithms, because we need a non-Clifford gate not only to complete a universal gate set, but actually for doing anything which is, classically hard. Because if it's just, a Clifford circuit, then now we can just, track our operators as they spread. Or for example, if we have two CZs and we, have some initial a stabilizer of the state like XII that we're tracking, this just, goes to another poly operator XZZ here. We can just keep tracking these operators, but every time an operator hits a CCZ, then now it goes into a superposition of operators. And now we get not only operator spreading, but also operator entanglement. And we have to track more operators. And so, every time we do, so the number of operators that we need to track grows exponentially with the number of non-Cliffords that we apply. And kind of state-of-the-art Clifford plus T simulators can handle, roughly 64 T-gates or like 16 CCZs. So that's kind of the relevant scale. So what we're going to explore here is if we can generate, complex states by using three-dimensional codes. So three-dimensional codes do gain transversal non-Cliffords, like a CCZ, for example, but they lose the transversal Hadamard. But we're still going to explore these in terms of, whether we can generate kind of complex states and what types of algorithms can we efficiently realize. And here, what we're doing is we're making these 832 codes that have been popular recently. And, it's 8 physical qubits that encodes 3 logical qubits to distance 2. It's distance 2 in one basis, distance 4 in the other. And what these logical operators look like here is that there's these X faces and Z strings encoding these 3 logical qubits. And what's so remarkable about this logical encoding is that we can do, really simple entangling gates on the logical qubits that are, they're already living in the same space. They're already kind of overlapped on the same physical qubits. And so it turns out that we can, for example, do a CCZ gate on the logical qubits that are encoded within the block just by doing single physical qubit T gates on these 8 physical qubits. And that sounds like cheating because we're going to generate entanglement by doing single qubit gates. But it turns out it's not cheating because we're also going to intersperse this with doing transversal C0 layers, and that's going to pay back our entanglement credit. So we can do, again, this internal CCZ and CZ gates. We can do C0s between triplets. We can also very easily do this kind of permutation-based C0 where we just shuffle qubits around, and that actually turns out to realize the C0 between these logical qubits. And also, here we're studying, efficient generation of kind of complex states, but this can also be made universal simply by doing measurement and feed forward on an initial plus state in order to teleport in a Hadamard. So there's many ways of also injecting a Hadamard with these 3D codes. And we make here 16 of these 832 logical blocks corresponding to 48 small logical qubits. Now we start to program complex quantum circuits between them. And what this looks like here, specific circuits that we implemented, is that we encode a logical state plus. We do this parallel, CCZ and CZ gates within the blocks. We can also do the C0s within the blocks. But then we do C0s between blocks using motion. And then we kind of repeat this using these non-local logical connections. And what we realize here are these kind of like scrambling or like quantum advantage type circuits where we're going to do, sampling on the output of our complex state. And in particular, to get fast scrambling, and also because it's, really fun to say, we're going to entangle everything on a hypercube. So we take these logical blocks, entangle them on this 4-dimensional hypercube, but each block is, a 3-dimensional cube of physical qubits, and this makes a 7-dimensional physical hypercube. And here we're again using up to 48 logical qubits, 228 logical 2-qubit gates, and 48 logical CCZs. And it turns out that, so this is an IQP plus C0 circuit. It turns out our collaborators showed actually mapped to another IQP circuit, and we kind of have done a variety of other analysis in this way, in particular, Marcin Kalinowski, Michael Gullens, and Dominic Kinglater. So, okay, for this kind of, quantum advantage type experiment, what we're going to do is sampling, where we do this complex quantum circuit, make projective measurements, and then compare our output distribution to the calculated distribution. And then we calculate the XEB, which is the sampling score, which is just this weighted sum of the expected probabilities with the observed probabilities. And it turns out that it actually is roughly, well approximates the fidelity for IQP circuits. Okay, so this is what the sampling output looks like. Here we're looking at 12 logical qubits where we can still plot, the whole distribution of the Hilbert space. So we have these 2 to the 12 possible logical outcomes. And, a successful sampling experiment corresponds here to having a finite overlap between the measured distribution and the theoretical one. But what we can see is that, as we increase how much error detection we do, which here, because it's, it's an error detecting code distance 2, for this experiment in particular, we're doing post-selection to kind of increase the amount of error detection that we do. You see that the distribution starts to overlap with the theoretical one better and better. And quantified by the XEB, we see here that as we kind of throw out more and more of our data doing its error detection approach, then the XEB here improves to a score of 0.7, which for these 12 logical qubits in this kind of a relatively complex circuit for 12 logical qubits is quite a high score. And I want to zoom into the data a little bit more because I find it kind of amazing. And here is the total output probability across these 2 to the 12 logical possibilities. And you can see that across this entire Hilbert space, the fidelity is not perfect, but everywhere you see this kind of theoretical orange peak, the data is there and kind of reproducing these features. But actually, as you zoom in further and further, if you track, for example, this red arrow, then what you see is as we zoom in further and further, even down to this kind of 10 to the minus 4 level, the logical outputs start to reproduce these tiny little wiggles in the theoretical distribution. And one of the things that's our understanding here is that logical qubits can actually have a very different type of error channel compared to physical qubits. Even though we have coherent errors on the physical level, it doesn't actually necessarily correspond to coherent errors on the logical level. And even though the fidelity of the circuit is not perfect, we get kind of we're able to reproduce these tiny little features because our current understanding that we're developing further is that the coherent errors in these logical circuits are highly suppressed. And it's kind of an example of the unique intricacies of kind of starting to explore things with logical qubits. And in scaling to, so that was with 12 logical qubits. Now we'll scale to larger sizes where we can't plot the whole distribution. And we go up to 48 logical qubits where we still get a successful sampling here because we get this finite XEB, and we see that this XEB score improves, as we continue to apply increased error detection. And in particular, this post-selected XEB that we get to is doing the error detection here is roughly a factor of 10 higher than state-of-the-art previous physical qubit implementations at the cost of measurement time, because we're doing this error detection approach here. It's also quite a bit higher than we're able to achieve in our system as given by this physical upper bound. And sampling is kind of an interesting problem for using error detection because you can't just improve the quality of your samples by measuring for longer. So even though we're measuring for longer, we're able to improve our score compared to what we would have been able to do without using this error-corrected encoding. Does anyone have any questions or? Okay.
There was a question in the Q&A about the amount of time it takes to collect the data. In this case, the question was for the GHZ state tomography, but maybe it applies also to this.
Oh, great. So for the GHZ state tomography was, I think, like a few hours, something on that scale, something on the scale of a few hours. Our experimental cycle time is 300 milliseconds. This is not going to, limit future quantum error correction. We're currently doing our experiments in this kind of pulsed mode where, we load atoms from a MOT, drop them, rearrange them, and then do, like a millisecond time scale unitary evolution. And then we reload all the atoms again. So, that's a separate conversation about the fact that, in the future, we're going to need to kind of continuously operate. But bottleneck by that 300 milliseconds, it's, a few hours for that. And then for this data, it's for the 48 logical qubits is a few days. Yeah.
Great, thanks.
Yes, question.
I have a question. Can you repeat the process to detect errors and improve the quality of the? It was a little bit quick.
Yes, sorry, I got a little too excited. So what we're doing here is we projectively measure all of the physical qubits. So we first encode the logical qubits, then we do our circuit, and then we projectively measure all the logical qubits at the end, all the physical qubits and logical qubits at the end. And then this gives us the stabilizers and the appropriate basis. And now we look at the stabilizer and then we see whether it did or did not have an error. When we're doing things with, for example, the surface code, we now infer what error happened and then undo it. Here, because it's distance 2, the best we can do is, okay, if there was an error that happened, we just discard the data. And here, this like increasing error detection, we're just increasing, how many errors happened. And so how, worried are we that an algorithmic error happened? And it's kind of like evaluating. Yeah.
So this is a process in the classical. So you gather all the data and then you do this process classically.
That's right.
That's right.
Yeah.
So it's not a quantum. It's not part of the quantum process.
No. I mean, well, no, but I mean, you could also call classical decoding is also like classical.
Right. No, it's not criticism. Okay, thanks.
Okay, fantastic. Yeah, no problem. Yeah, great question. Okay. Yes, another question, please.
So as I'm looking at your data and I'm comparing them to superconductivity, it seems that the gate operations are about 1,000 times slower. And then you also have an overhead to load the MOT, which is a little bit. So those are, and then there's maybe an additional factor of 100 that you have to do once for that overhead. Is that about right? You said
so. In terms of understanding timescales, yeah. So our current unitary evolution timescales for doing our circuits is like millisecond scale, and this is given by. So our gates are very fast, like 200 nanoseconds. The movement time is 100 to 200 microseconds, which is like a factor of 100-ish slower than the superconducting kind of clock. Let's call it 1 microsecond, and we can have a whole conversation about clock speed. But right, okay, and then currently we're reloading the MOT and rearranging the atoms, and we're not optimizing the speed of that at all. So it's currently roughly 300 milliseconds. There's going to be a transition in the field in the kind of coming year, probably, where people are going to switch to continuously operating on the atoms, and that kind of timescale will probably go away.
But there's still kind of a factor of 1,000 roughly. So the other question I had is you talked a lot about you can do kind of parallel control of this and multiplex control. And, thinking about the system engineering, I'm going to say you can do that because your qubits are a lot slower than superconductivity. The reason you can't multiplex superconductivity is they're too damn fast. Okay. And you just can't, you don't have enough bandwidth per channel to do much multiplexing. There's other things going on too, but it's kind of an interesting trade-off between speed and control here.
So I okay, I got it. But here's my viewpoint. So okay, clock speed. Okay, we can have. I'll leave the clock speed comment for later. I mean, clock speed will be important in the future. It's not limiting at the moment. But in terms of parallel control, I mean, with quantum error correction. So okay, regardless of the technical limitations that are or not present in different systems, with quantum error correction, we need a lot of qubits. We need million. And they all, half of them need to do a Hadamard at one moment in time, or half of them need to do a CNOT gate. I cannot believe that we're going to do this without parallel control in the future. So with any system, regardless of whether it's atoms or superconducting qubits, I think this parallel control is going to continue to be central.
Well, there's parallel control in superconducting qubits. You just have to control each wire, but you can do everything in parallel.
I think doing parallel control in superconducting qubits is central. I would agree with you. I mean, I think that I think that sounds great. I mean, because if there's going to be so many qubits, we need to control, and they need to do the same thing, then the instruction needs to come in parallel. So in whatever technical solution there is to that, I think that sounds amazing. Yeah.
Yeah, I think it's very interesting because there's kind of two underlying ways of doing things, contrasting superconductivity with this, which means they're very complementary technologies. But I agree, this is nice that you can move atoms around and complex algorithms. Nice.
And I would sooner give up, maybe I'll say one last thing and then I'll continue going. I would sooner give up the ability to do non-local connectivity than I would give up the parallel control. And I think that's going to be the central message of my talk, that in these other kind of approaches, no matter what we do, we need to have parallel control because all these qubits need to do the exact same thing. Yeah.
Great.
Okay. Is it okay if I run like 5 minutes overtime, Umesh? Is that?
That's fine. Yeah, we've had a lot of questions, so. Yeah.
Okay, fantastic. Okay, here's a movie of what this logical circuit looks like. So we're entangling everything on this hypercube here. So in the first 3 steps, we created these 832 cubes, and now we kind of entangle them in these higher and higher dimensional hierarchies, where we pick up these logical blocks, entangle them with each other. We move these logical blocks away, pick up this new group of logical blocks. All this time, we're preserving coherence in the storage zone, and then do the circuit all over again. Okay, and then it's gonna one more entangling it, and then we pick up these qubits that are in the storage zone, do this entangling, and then this one parallel, and then in this final parallel step, we now finish our 7-dimensional hypercube. So we studied here kind of sampling or kind of like benchmarking of our logical circuits, where we kind of structured things in this way that we can still simulate them, so we can actually benchmark our performance. But we're also physicists and we like to do physics. So we're also kind of exploring what types of interesting physics can we do with logical qubits. And here, one of the tools that we really like to use is these Bell basis measurements. And measuring things in the Bell basis is quite powerful. You can get, for example, the entanglement entropy in the system. You can also simultaneously extract all 4 to the n polystring absolute values. And here what we do is we do a scrambling circuit. And this very powerful tool is just fully compatible with doing logical qubits in a transversal C0. So we do scrambling circuits on 2 copies of our 12 logical qubits. Then we again do this 2-copy measurement between them. And here what we're plotting is this logical entanglement entropy as a function of subsystem size. And by applying our error detection, we get here this really clean page curve where we can see that the entanglement builds and builds and builds for this highly scrambled state. It's actually a fast scramble of the circuit that we run. But then once it gets to half the system size, this system starts to realize it's inside of a quantum simulator, and the entanglement entropy starts to go down. And we're using this error correction here in order to be able to see cleaner types of, for example, quantum scrambling physics than we've been able to see before using our physical qubits. And it kind of shows that logical qubits, if you're clever, can already start to be used for doing various interesting physics and quantum information explorations. I think I'll skip this. I don't think I have enough time. There's many, many different ways you can analyze the data and measure, for example, the magic that we imprint inside of this logical circuit. Okay, so now I'll switch to summarizing. Okay, I think I should finish on time, actually. So, okay, so what we see is that our quantum operations improve with code size, and we make surface codes that are as large as distance 7. We can start to do fault-tolerant algorithms and characterize our zone processor, and start to study complex scrambling circuits with these small 3D codes, exploring both, sampling, but also exploring the physics that we can study with that. And so the natural question is, what did we learn from, doing all these experiments, and where do we go from here? So in terms of, listing some of the, bullet points of lessons that we learned from our first generation logical processor, the one that I cannot emphasize enough, that I guess at this point I've said many times, is that it's really the control over single logical qubits as the fundamental units in this processor that dramatically reduce the costs of building this type of device. And if you're, this is a, experiment that's built and operated by, a few PhD students and postdocs in a lab. And, here, if you would have come into our lab while we were, making these logical GHG states, what this looks like is we have, these, 10 logical qubits, and we're programming, these logical CZ gates between these qubits by just, moving them into each other and then pulsing this, one global laser. And we're really focused on kind of doing this efficient logical qubit control. And, that is really what was central to being able to do these experiments by, really simplifying the control problem. Another important lesson is that instead of considering individual logical qubits, it starts to make a lot more sense to consider algorithms together as a whole. And here, this correlated decoding is something that we've been able to use to improve the fidelity of our circuits. Another bullet point is that logical qubits, are not literally qubits. They're many-body systems, and sometimes they don't behave in the ways that we, quite natively expect. So, for example, the Bell state fidelity, the logical Bell state fidelity, is not just given by, logical spam times a logical gate fidelity. It's a more complex process than that. But so that, can be unfortunate, but there's actually also pleasant surprises sometimes working with these logical qubits where, we get, for example, inherently digital operation where the coherent logical errors are suppressed, and we, primarily convert the errors into an incoherent channel. And, it appears that there are genuine examples where logical qubits can already be used to outperform physical qubits at interesting problems. Here, a note is that this discrete gate set is a curse because it limits the types of things you can study, but it's also a blessing if you can design your problem around it. If you have a unitary evolution that falls close to this discrete gate set you want to implement, and it's actually one of the few types of unitary evolutions the logical qubits can even realize. And there's, I think, many more opportunities going to be here for doing these early generation logical algorithms. So that's what I would kind of describe as our early generation logical computations, but something that I think is emerging across the neutral atom community as a quite exciting and unique opportunity is this ability to build medium-scale error-corrected devices in the near term. A really important key step here experimentally that will be very important is not only removing entropy at the end of the algorithm, like we're doing here, but removing entropy during the algorithm and seeing that we can actually increase the depth of a quantum computation. So that's an important thing we're working on. Just by increasing laser power, these existing techniques that we have here can be scaled to roughly the scale of 10,000 atoms. The physical errors, like in the two-qubit gate, can be reduced to the 0.1% level. Continuous operation, as we've discussed, will be critical in these systems. And there's going to be many, many unique opportunities. People asked about different atom species. And people are exploring many different diverse things across this neutral atom community. I think it's a pretty special community. And people are, for example, exploring erasure conversion, different atomic species, using bias, different types of efficient optical control. And what's so amazing about these systems is they're so modular that we can really take the different breakthroughs that different groups make and kind of combine them together in kind of improving what we can do. And I think all of these things together will be able to create a device in the kind of near term that will be able to give us something on the scale of 100 logical qubits that can do something on the scale of 1 million logical gates without having an error. So this will not necessarily yet, solve all these really big problems that we have in mind. But if we are able to build this medium scale error correction device, it will be a really new tool for scientific discoveries, and it can really help accelerate us along the path to doing large scale quantum computation. And I think, in our perspective in the coming years, these devices will unlock, kind of completely new studies of quantum mechanics where, we start to kind of study, some of these, and some kind of important theoretical questions that we start to run into here is what types of algorithms do we even study with having 100 logical qubits and 1 million logical gates? And how do we also structure these for efficient quantum error correction implementation, similar to how we did things with these 832 codes here? And finally, we're also, excited not only about these medium scale devices that seem to be on the horizon, but also thinking about really large scale logical devices, getting to the scale of, 1,000 logical qubits with, corresponding to millions of physical qubits operating coherently for days. And, this is something that, to be honest, we have ideas for, but is still, quite daunting numbers. And we do have ideas that we're exploring. So for example, LDPC codes can really reduce the overheads we need. We can have power efficient trapping in order to control many more atoms. And we're also, thinking about different ways of connecting the modules. But the reason I want to emphasize that this still sounds like a really hard challenge, although achievable, is that we should really be pursuing all of the possible breakthroughs that we can find, both in terms of the hardware design, but also in the code and the algorithm design, and doing this co-design and seeing if that can really further reduce costs. And, at least in my perspective, the experimentation that we do in the coming years with these early generation logical devices will probably reshape the way that these large scale logical devices actually end up getting built. Okay, thank you. That is the end of my talk. And I'd like to thank the kind of amazing colleagues that all participated in this work. Thank you.
Wonderful. Thanks, Dolev. That was beautiful talk and very inspiring. So let's see if there are questions, and then we'll move on to the panel. So let's see. There were a couple of questions in the chat. I wonder if so there was Vijay who asks, it's not obvious to a non-expert why the mod has to be reloaded every time. Is it because the atoms get untrapped periodically?
Oh, yeah. So I mean, already we could trap our atoms and then keep them, and after the image, and we could just run the experiment again. And we don't, because that's not how our field has historically developed. And there's going to be a phase transition in the field where people now will want to start doing this. So yeah, I mean, if you want to reload atoms from scratch, you have to be very careful with making sure laser beams don't hit your other atoms. But these are solvable problems that people across the community are working on. Yeah. On what machine were these experiments done? This was done, just in a university lab setting inside of our Harvard basement. So we can define the specs, but that's yeah. The page curves fit pretty well. Sorry, I'm just going through the questions. Is that what I should do? The page curves fit relatively well to the theoretical analytical formula. There's a slight blip in the middle where they go a little bit higher, but for the smaller system sizes, they fit better. Should I keep just answering all these questions? I'm happy to just...
Yeah, there's somebody in the audience. Colin wishes to ask a question, maybe.
Oh, sure. Mm-hmm. Yeah, please. I don't know how I'm supposed to do that.
Oh,
allow to talk. There we go. Mm-hmm.
Colin, you're mute. If you want to ask your question, unmute yourself.
In the meantime, while Colin is waiting, I'll answer just some of these other ones. So it's not necessary to well, I mean, the readout beams were pretty robust. I mean, if some of the atoms are scattering, 3% faster than some of these other atoms, it's not really something we're sensitive to. So no, we don't really homogenize we just have like a simple Gaussian beam used in this readout. So how worried are we about potential catastrophic errors? So, I mean, with any of these quantum devices, it's true that you're very sensitive to correlated errors when you're trying to do quantum error correction. And it's true we have these, for example, parallel operations. But, to the best of our knowledge and kind of what we've characterized, which we also characterized in the supplement of our high fidelity gates paper, we do not see large-scale correlated error events. Like, for example, it's not that sometimes the laser pulse just spontaneously doesn't come out on all of the atoms, which would, of course, be a catastrophic error. Similarly, with any quantum computer, you should never unplug it from the wall. So, I mean, to the best of our knowledge, I mean, all of these are kind of classical problems that are highly solvable. Yeah.
Ivan, too.
Yeah. Hi. Well, thanks for an amazing talk. One question about the sampling with the IQC circuits. It was kind of amazing, really amazing that when you zoomed in there and you saw, the level of agreement with the theory. I wonder if you made some comment about the difference, at the sort of physical level of the errors versus the sort of error channel that you might expect, at the whole level. I mean, is there any ideas about that? I mean, is it close to something that looks like a depolarizing channel? I'm just shocked that the most probable outputs are not in any way shifted.
Yeah.
They're reduced in magnitude. The sort of the visibility of the fringes was changed, but where the high intensity was not shifted at all by errors. You have ideas? Is that expected? Is anyone thought about
So it is expected. So I'm embarrassed because I'll tell a story involving Peter Shor, but Peter Shor is here. So the story I would like to tell is that when people first were developing quantum error correction, there was this argument between Peter Shor and Landauer saying that it's just analog computation. But the response is that the computation is analog, but the errors are digitized. And I do think this data indicates that. And we're working on quantifying it. When we've done this before with physical qubits, it also, the distribution heights change, right? So, I mean, you have a small coherent error and then it just kind of dramatically changes the shape. I mean, the other thing is that all of these data was taken blindly. I mean, we set up the circuit and then in any experiment you optimize, but we optimize the stabilizers. We don't even look at the logical qubits. The 48 logical qubit data we took on just a first attempt after optimizing the stabilizers. We don't even, and then later we figured out how to simulate it, right? So it's, I mean, I think that's also a remarkable aspect of practical operation with logical qubits. Yeah.
Thanks.
Good. Are there any other questions?
I had one, Umesh, if I can.
Yes, please. Sure.
So this is just very even speculating beyond what you were saying. Is it, if I understand correctly, everything you do right now is atoms arranged two-dimensionally. Is it crazy to think of having multiple layers and almost a three-dimensional packing eventually?
So not crazy. So I mean, 2D is always going to be the most natural. I mean, we live in a three-dimensional world and you always need one dimension to access things from. I mean, that's also going to be, I mean, that's true also with our classical computer chips. So that is something that always will be natively the easiest. People have done remarkable experiments, for example, in the Brouwer group, where they, for example, made a 3D Eiffel Tower. So it's definitely possible. And it's interesting to explore. I mean, these are the types of things that are really interesting on an architecture level. Yeah, absolutely.
Thanks.
Mm-hmm.
Excellent. So, yeah, go ahead. Sorry.
I was going to ask if anyone wants to ask about clock speed, but then maybe I'll make a quick comment about clock speed because John brought it up earlier and I didn't get a chance to fully talk about it. So for these medium scale logical devices, when we're talking about doing 1 million logical gates, it takes and we can do parallelizing of these logical gates. Also, we get this factor of, so okay, our systems currently are slower, limited by the movement time, slower than superconducting qubits. where it's like 100 microseconds for the motion compared to, for example, and that's the bottleneck compared to like a 1 microsecond clock cycle in superconducting qubits due to the readout currently. So that's a factor of 100 slower, roughly. There's two savings though. One is that we get a factor of D saving from doing this transversal gates, roughly. We get a factor of D saving there. And for certain algorithms, you actually get even more savings by the fact that you can just directly connect these two logical qubits without any routing problems. And that depends on the algorithm. But both of these can have pretty dramatic savings. So already I would say that they're kind of comparable just by including those in terms of kind of like the relevant clock speeds. If the distance needs to be like 30, for example. In practice, what I would say in terms of clock speed is that with these medium scale logical devices, if we're doing 1 million logical gates and we can parallelize and it takes roughly 100 microseconds per logical gate, then then at that point, the circuits are going to start taking, scale of 1 to 10 seconds. And at that point, it's going to be like a BC experiment, which is, it runs and you can get data out of it. But then the experimentalist is going to sit in front of the computer and be pretty annoyed by how long it's taking. And that is, I think, when, we're going to start, really rapidly speeding things up. I mean, we do have ideas in terms of how to speed things up. That's when it's going to be the time to kind of really implement them into the kind of state of the art implementations, because if you need to do 1 trillion gates, you want them to be as fast as possible for sure.
Great. Okay, so thanks a lot. So maybe this is a good time to move on to our panel. So if you could stop sharing, Dolev, and we'll get the videos of the panelists pinned. In the meantime, let me just say that, make a quick announcement. So we are not going to be doing this colloquium every week. There's a quantum program at the Simons Institute going on this semester. And so, for example, next week, we have a workshop on advances in quantum error correcting codes. So the next colloquium will be the week after that, and it'll be Oded Regev talking about his speed up of Shor's factoring algorithm. Okay, so let's see. Okay, we have a panel here, and it's as you can see, it's a very distinguished panel. It hardly needs any introduction, so I'll keep it very, very short. We have Barbara Terhal, who's joined us many times before. She works on quantum information theory, in particular quantum error correction and fault tolerance, which is very relevant to us today. Jeff Thompson had given a talk earlier. He's an experimentalist working on, among other things, Rydberg atom arrays, and he had spoken about converting general errors to erasure errors, which I'm sure will be relevant today. Of course, John Preskill needs no introduction. He's okay. I like to think of him as a high energy physicist who jumped into quantum computing right in the early days, and he's the highest energy quantum computing person around. He's worked on every aspect of quantum computing. And Misha, of course, he's both a theorist and an experimentalist, and I think he's clearly the driving force behind this great blossoming of neutral atom arrays. It's quite an accomplishment. So maybe we'll jump straight to it, and I'll ask the panelists to give speak for a few minutes each about both the reaction to the talk as well as where we might be going in the future, etc. So, Barbara, maybe.
Okay, sure. Yeah, well, I mean, I think it's great. I think everybody's very enthusiastic, and it's very nice to see, all this mobility, and also the sort of that all these atoms are very identical, which is not something that you have for superconducting qubits and so on, right? Which gives an advantage to play them in parallel, so to say. One thing I think from having some contact with the superconductivity community and trying to do error correction there, I think what I would like to understand more is more deeper characterization of every component. Also, now maybe some sources of errors are still below the radar screen, but for theorists, sometimes this can be important to know, right? Even if the moving, when you move stuff, there has a little error, then you say, well, maybe I have a very fancy code for which I do not a lot of moving, but then that is going to be important. The other thing, of course, is something that I've worried about with superconducting qubits is leakage, and you have in addition loss of atoms, right? And what's not entirely clear, but I think you have addressed these points also in talks and so on, like during the Rydberg gate, the 2-qubit gates, whether you can lose an atom, what the probability for that is, and so on. So, and of course, as you say, that the big thing, I mean, it's kind of a dull thing to say, oh, we need to be below threshold. But I don't know whether you think that with the current components, you could be below threshold for the surface code, or whether you have an estimate for that. And then the other thing is that fancier codes may have other advantages in terms of logic, but maybe then their threshold is worse. So it is very important to know. Yeah, I know you have to do other things for this measurement, that you can measure stabilizers multiple times. But this characterization of noise is important to know how close you are to this target of preserving your logical qubit and, doing better with larger distance. So yeah, those are a few comments. Of course, interested to hear your thoughts on this. Yeah.
No, please, Joe.
You're talking to me?
Yeah, I thought you
Okay.
wanted to. Yeah, please.
Well, I mean, first of all, applause. It was a terrific talk, and it's an amazing experimental achievement. A lot of points have been made. I'll reiterate some of them. It's very likely that we're going to need fault-tolerant quantum computing to achieve practical quantum advantage. There are interesting ideas about noise mitigation, but they're not going to carry us far enough. And for the next maybe 10 years, I think the two avenues where we're expecting to see remarkable progress are simulation of many body physics with the platforms we have, and progress towards quantum error correction. Not just with Rydberg atoms, but also with some of the other platforms. And there are opportunities, say, with superconducting qubits to explore things like erasure conversion and bosonic encodings, bias noise. And in addition to Rydberg atoms, with ions too, we can achieve high connectivity, either through shared phonon modes or through movement. And in all these settings, one thing that's really going to be key is continuing to improve the fidelity of the 2-qubit entangling gates. We'd like to see improvements in error rates for error correction to physical error rates for error correction to really take off. Well, one important point is that for superconductors and for ion trap processors, we have seen demonstrations of repeated rounds of syndrome measurement. And we haven't seen that yet in the Rydberg atoms, though we hope to soon. We'll need the ability to load fresh atoms, which is under development. Now, Dolev made the point that co-design is becoming very important, and I'd like to reiterate that as well. And I think that's what we're seeing increasingly in the efforts to advance quantum error correction, that the error correction schemes can, to some degree, be adapted to the features of the hardware and are suggesting new approaches to building the hardware and operating it. Of course, for the theorists, there's a lot to do to come up with better coding schemes, and a big opportunity is the protocols for achieving logical gates using some of the efficient coding schemes that have recently been developed. I think to me, there's a cautionary tale, which is interesting. Maybe 5 years ago, Rydberg atoms looked very interesting from the point of view of simulation of many body dynamics and many body physics, but we weren't thinking of them so much in the context of gate-based quantum computation until those Dolev spoke of the Harry Levine et al. Work where they developed those gates, and then things really took off, and that could happen for other platforms too. We might see with spin qubits or maybe photonics, and 5 years there will be a key development which will point us in new directions. I guess so. The summary is, please, higher gate fidelity. Let's see loading of fresh atoms soon. and better codes theorists and better ideas about how to do interesting physics with what we have and what we're going to have. But finally, I want to talk about speed again. It's come up several times, but it's key to the long term. It may be that we are entering now the age of movement, that over the next 10 years, by reconfiguring Rydberg atoms and moving ions around, that'll be the frontier of quantum error correction. In the long run, we're going to need much faster logical gate speeds than we're talking about now. The movement has been remarked. What's slowing things down? Maybe with Rydberg atoms, in 10 years, we'll be going back to geometrically local protocols because the movement is just too slow. We're going to care when we're doing deep circuits about factors of a few orders of magnitude in logical gate speed. It'll be a big deal. So focusing on improving the logical cycle time is going to be really important in the long run.
Jeff, would you like to?
Sure, I'd be happy to. Well, so first of all, I'd like to, thank Dolev for this very impressive talk. These experiments are super impressive, very clearly explained, and very cleverly designed, and sort of provocative about what we can do in the near term. Maybe there's kind of two things that I would like to set up for in a discussion, both of which have been touched on by Barbara and John before. The first is sort of about the error model and how it comes together. Basically, the thing that's amazing about the theory of error correction is that you can get from 10 to the minus 3 to 10 to the minus 10, and it's sort of the only way we think you can do that. But that relies on a bunch of assumptions about the not only error rates, but certain details about how the errors behave. And you can enumerate these, like the lack of correlations and being able to do things in parallel so you don't accumulate idle errors, et cetera. But what we've seen from other platforms is that nature is sort of fickle and will find a way to do things that you don't understand. So the exciting thing about actually building logical qubits and running fault-tolerant, syndrome extraction and gates is actually seeing, okay, do the benchmarks that the whole community has basically been doing for in every qubit platform for 20 years now, do they actually translate to this logical level? And so I'd be curious what you think about that. I was a little surprised that wasn't on your list of what are the main lessons from the first logical processor. And the second point I'd like to make, I think just a comment on is, clock speed came up a few times and you brought it up on your own. In my opinion, it's a little unfair to say that it's 100 times or 1,000 times or whatever times slower than superconducting qubits, because fundamentally the clock speed is limited by the sum of all the operations that you have to do in some deep circuit. And right now, all the operations, including continuous reloading, have just not been demonstrated. So a superconducting qubit processor can now do an experiment that in some amount of time that current neutral atom processor can't do in any amount of time. So I think the only defensible thing about this clock speed right now is that it's infinity, this ratio. And I think when we start to bring online things like continuous reloading, then it's very likely that could be the bottleneck for clock speed that we have to talk about. So there's really a logical clock speed, which is just this kind of the slowest of all these components. And that's the thing I think it's important to keep in mind.
Great, thanks, Misha.
So yeah, I guess I can shouldn't really express my opinion about Dolev's talk since I've been working on it for quite some time. So, but needless to say, as you guys realize, we are super excited, and we really hope that this development really put the entire field on a kind of new trajectory and will accelerate the progress across all platforms. But we are clear-eyed about the challenges ahead, and we realize there is a lot of work to do. But maybe the lesson that we're really learning here is that this kind of building a large-scale quantum computer is both an exciting error-corrected quantum computer, is both exciting engineering challenge, but it's also an exciting scientific challenge. And a lot of these things, which for example have been kind of mentioned already, you can view look at them as challenges, but also kind of an exciting opportunities. And for example, in principle, we have all ingredients to run, to be below threshold for, for repetitive error correction, many rounds and so on. But we certainly hope that we can utilize, some of the kind of, our understanding of errors to, first of all, reduce them further. So there is no one, tells us that this 99.5 is a limit, so we believe, for example, that there is a fairly clear path to 3 nines, but, we have to demonstrate it, first. So likewise, these kind of ideas of this leakage and so on, they, of course, on one hand, challenges, but also, opportunities, as, for example, was illustrated by the work of Jeff. And so what we hope also is to devise codes which maybe have higher effective thresholds, so by taking an advantage. And this is, in these current experiments, this is basically the surface we didn't even scratch, even though we knew that these things kind of are present. So I do think that this, this question of speed we should take, seriously. And I mean, I agree, of course, I totally agree with, with Jeff's point about, for example, continuous reloading, being an important ingredient of that. But I actually expect that there will be a very fast progress in the community to actually kind of start running these experiments continuously, because there are just very well-developed techniques, that people already kind of, demonstrated in other contexts. But of course, we need to combine them with what we do, right? The proof is kind of in the pudding. And in terms of just, let's say, kind of a cycle speed, let's call it in this way. So there are various considerations here which kind of range from, let's say, kind of, algorithms, like, for example, Dolev mentioned in passing that some of these transversal gates appear to have a property that you don't need the rounds of error correction. So, I mean, that, if you can do that, that immediately gives you a substantial speed up. So at the same time, we certainly, hope that both the speed of movement, but also the speed of readout can be greatly enhanced. And in that case, maybe I, disagree a bit with the remark by John that it's a trade-off between speed and parallelism. I don't think so. At least, this is something that I don't see in our case as being in our system being the case. So, and I'm certain that this kind of the speeds of these techniques will be improved. And then finally, regarding John's remark is that maybe this movement is great, but maybe at the end, like you don't, maybe we need to go back to stationary qubits. So this is like, it's not black and white, so, at least kind of my current thinking, our current thinking is that, this movement will be, absolutely essential, even in the long term, but maybe you don't need to move so much. And that brings us to the ideas of, for example, better compilers, maybe sometimes using different species of atoms. These are all the things which community is working on. I think all of them are very exciting opportunities.
Thanks, thanks, Misha. So maybe I can ask a couple of questions as a naive theorist. So it's hard for me to. I mean, I hear these issues about speed, and as well as the, clearly it's very important to do continuous reloading of atoms, to get fresh qubits. So I wonder if you can sort of put some numbers on it and help me understand whether, what the current bounds are and what sort of trajectory you would expect. So one, I guess the things that I've heard that, that where the slowness comes in, one is in the readout, and I wonder if you can address what slow means here, why it's slow, and whether it's inherently, whether there are any inherent limits. The second, of course, is this transport speed. Again, what's the order of magnitude, and what can one hope for in the future in terms of that? And the third, I guess, again, has to do with this continuous reloading, but again, in terms of the loading to begin with, I imagine that would, the loading speed, whatever you can achieve, would be a bound on the throughput if you do continuous reloading. So what would that be now, and what would you hope for in the future?
So should I answer those questions in particular, or the kind of the going through? Okay. Great. So
this since these seem to be the important things, just to understand what sort of trajectory you're hoping for, and where things are, and where you would hope for them to go to.
Great. Okay. Yeah. So in terms of readout speed, so here the readout speed was 500 microseconds, which was, essentially an arbitrary choice. We've also done it as fast as 200 microseconds without fidelity degradation. It was just a bit more stable with 500 microseconds. So, the fundamental limits in terms of how we do it is kind of at the scale of tens of microseconds, depending on the specific details of the atomic transitions. And also, we would need to develop slightly better electronics in order to get the image out faster. But I do think that kind of, in my mind at least, I think of kind of 50 to 100 microseconds in terms of the whole process. And one also should be pretty cautious in terms of how we think about readout speed, because it's not a superconducting qubit system, which looks like measure the qubit, reset it, and then use it again. And I also use this to address a different comment, which is that, the way in which we're doing repeated syndrome measurement, for example, is very flexible. And, all of the things we've demonstrated are completely compatible with doing repeated syndrome measurement by using, fresh qubits and also reusing qubits. And we haven't done it yet because we've been busy. But then, for example, in thinking about readout speed, you should think about, at least in my mind, with our approach, I think about 50, 100 microseconds. But you should think about it not like, oh, you need to measure a qubit and then bring in the new qubit. You can bring in new qubits as you're measuring. That's one difference. But also people are exploring different ways of doing faster readout. For example, there's fast ensemble techniques developed, for example, in Bluvstein's lab. There's also cavities. So I think if that's really a bottleneck and you need like a cavity readout zone for super fast readout in a specific time, then I think that is something that could be achieved. In terms of the movement speed, I don't think it'll ever be as fast as the 2-qubit gate. The 2-qubit gate will probably be roughly 100 nanoseconds in the future. It could possibly be much faster, but that's kind of the timescale I have set in my mind, also for the single qubit gate. And we do have approaches that we could make the movement much faster, but it's never going to be that fast. But also, if you're not moving, then there's also these other complications. So I kind of agree with what Misha said, that it's not, I think, going to be, completely black and white. And in practice, if we have this, million logical gates and you want to get data, or like you have like a billion logical gates, in practice, it might depend on what you're doing, what your trade-offs are in terms of like fidelity or speed or kind of convenience or space-time cost. So I think it's an overwhelmingly complex space of things to explore. And once we actually have these devices, I think there'll be really interesting exploration of that. And then could you just remind me this comment about throughput for the continuous reloading, what you had said, what the atom rates are?
Yeah. So if it takes X amount of time to reload, from scratch, or load from scratch, then I would imagine that X translates into some bound on the throughput if you're going to
that's right.
capacity. And so what would you imagine that would look like once you get the continuous reloading up and running?
So there's many different, numbers that one could give, and the kind of different origins. The number I have in my mind personally is like kind of scale of 10,000 atoms per second for us to be able to run these kind of like deep medium scale logical devices with like 100 microsecond logical gates. And we could, there's different ways we can parameterize this number. How many of the qubits are we reusing, and so on and so on. But I think that's something that's quite attainable. There will be some work that needs to be done. The atoms are never a limitation. People in like ultra cold atom communities have demonstrated, transporting 10 to the 5 atoms per millisecond across 40 centimeters. There's so many atoms. The problem will be to trap them and sort them very quickly. And that's, a classical problem of how to most quickly sort things into, for example, a 10,000 atom defect-free grid. And I think that will be pretty attainable at that scale. To get to, doing 1 million physical qubits, I think there's many things that will have to be different about the way we're thinking about the system. And either, if it's in one system, then that will have to be different, or it's like connected photonically. If it was 1 million qubits, then it would have to be much faster, right? But it's a whole different beast at that point. Yeah.
But delivering, just in plain numbers, every time we start these experiments, we create a magneto-optic trap, right, which has 10 billion atoms, right? And it takes much less than, it's sub-second, right? So, if you can basically kind of sort them and deliver them, it's in principle all classical, things. And what Dolev is saying, we have a very clear path how to deal it with maybe, tens of thousands of atoms, but potentially similar techniques will work for larger systems or potentially slightly different. So that's a consideration.
Great. There was one other thing. Oh, sorry, Jeff first. Yeah, please.
So I think maybe this is not exactly the right way to think about it, but one way to think about kind of these measurement speeds and gate speeds and whatnot is that fundamentally, when you're doing error correction, every measurement you get a bit of sort of entropy out of the system, and you can't be applying gates like too much faster than that, right? There's kind of the usual surface code thresholds we quote are basically one measurement per gate or one measurement per few gates. So as I see it, if you're loading 10,000 qubits per second and you're doing these measurements, these 500 microsecond fast but destructive measurements, you basically get 10,000 bits per second of entropy out of the system, and that is, Sycamore is 50 million. So I think this is really a key challenge that is maybe a better thing to focus on than the speed of individual gate operations.
Can I respond to that really quickly?
Please.
So I agree with that estimate, but then also, at least in my mind, we're going to make the readout non-destructive in the near future. I mean, it's pretty wasteful. You already know the atom is there. There's many ways to make the readout non-destructive, just like when we do normal imaging. So that's part of my consideration. But yeah, I'll fully agree with what you said, though.
Great. Just backing up a little bit, to me, what's striking also is that somehow what you're doing is also making us rethink quantum computer architecture in some way. So so is this is the area of quantum computer architectures now sort of is it much more in play? Where do you see it going? Is there any comments on that?
Yeah, I mean, I think I think it's very exciting. I mean, I think people have been working on, you can find papers, for example, where people have realized the quantum von Neumann architecture, or people, propose a quantum von Neumann architecture. But but I think now, it's like prudent, right? And so, yeah, I think the architecture makes a huge, huge effect, both in the theory and the hardware. I think that's some place where we're going to have a lot of innovation in the coming years and beyond. Yeah, just like we do with normal chips.
And compiling, for example, these circuits. So to me, it's a kind of, minor miracle that, what we have done actually worked out, just in terms of just how the circuits were compiled basically by hand. And clearly there are tons of opportunities of really going forward to how to improve and optimize it. And, it touches on many things which we have actually discussed here. So I think it's super exciting frontier.
Oh, Barbara?
Yeah, I guess by architecture, Umesh, you mean that, maybe in the future we'll have this dense quantum memory with lots of logic qubits in storage, and we pull a few qubits out of storage, or do you mean the mobility? Of course, there are various aspects of this.
Yeah. So what I had in mind is that I was speaking somewhat more naively. I was thinking, look, computer architecture has evolved. Classical computer architecture evolved over a period of time. There was and of course there was a there's a it was tempting always to sort of say, well, now with quantum computing, it's going to be sort of some mashing together of classical architectures with quantum capabilities, and you sort of rethink some parts of it, but to me it seems sooner or later we'd have to go from mashing together classical and quantum in this way to sort of saying, look, maybe we have to rethink quantum computer architecture altogether, and maybe this is a step along the way of this process, and possibly we need to there are going to be several steps in terms of rethinking what a good architecture is. So
should I answer, or?
Yes, please.
So okay, maybe I'll give maybe various answers. Maybe Misha has more thoughts, but in terms of thinking about the quantum computer architecture, like for example, to do like error corrected sampling, like if one were to do this, with surface codes and teleporting in T gates, it would be way more expensive. And so here, I think we found a way, which is, quite inexpensive to do like this task or studying like this scrambling circuits. Now, if you have a really complex algorithm or a whole host of algorithms that you want to study, we've only even begun to barely think about what they are. I mean, people have thought about it a lot, right? But in terms of like, once you actually have it, it's different. But then also even how to implement it, how to do this like fault-tolerant compiling is so complicated and kind of a new thing that's really exciting that, I mean, now you have different parts of your processor that are supposed to do different things like addition, maybe something else is happening here. I think I wouldn't be surprised if we're using 5 different types of error correcting codes at a time. So I mean, I think it's very complex on a theoretical level. On a hardware level, my perspective is that, I mean, of course, we're always going to integrate with the classical devices. I think one way in which I've been rethinking like how I think about quantum devices is that like it's really that the logical qubits are the key building block. And in classical devices, the bits themselves are protected, and we operate on bits. Here, the logical qubits are protected, and we operate on logical qubits. So I think they have to be kind of the fundamental unit in an architecture. I mean, that's obviously kind of a big part of my perspective. And I think that kind of coming down the line in, for example, 5 years, we will have done a lot of exploration, at least with neutral atoms, about what the different building blocks are. We'll have still new innovations with the building blocks, but a lot of the innovations we'll have is thinking about how to stitch these building blocks together in this exceptionally complex problem. I don't know if you asked, I think, a very deep question, Umesh, that I think I only barely understood the surface of, but I'm curious what Misha's answer is.
No, I totally agree. I think that this co-design will be a key to kind of moving forward. And there we need to think about the algorithms we want to execute, the error correcting codes, compilers and implementation. And so, and indeed, the fact that, this quantum computer should work along with classical, this is actually something we really need to kind of, think, carefully together. For example, this idea of correlated decoding, effectively what you do, you actually push some of the tasks, you lower the requirements on your quantum computer by making decoding harder, right? And, eventually, there will be some trade-offs, here. But I think to me, this really is an exciting opportunity that we can, both develop these ideas and hopefully try them in a lab.
John?
Well, I don't know. I was going to change the subject, but maybe Barbara.
So maybe Barbara had something to say quickly, and then
well, just something about coding that there is, of course. I think it's very nice that because qubits are mobile now, we have more opportunities to come up with clever codes. It's not necessarily easy, right? Because you say, okay, I have a 3D code, it has a transversal T, great, but then its threshold is lower. There's a beautiful tetrahelix code that I think that's useful for these IQP sampling. I'm not sure that we know, how noise, what noise it can tolerate. So going to higher dimensions and fancier codes has advantages in terms of logic, but the surface code has, it has some, nice properties. I mean, there's a reason it's not going to be pushed away that quickly, I think, for some things. Not for logic, of course, is bad, but for other purposes.
Sorry,
okay, John.
Yeah, well, look, I realize that computer scientists' eyes glaze over when we talk about atomic physics, but actually, David DiVincenzo brought up the point of whether there are alternatives to rubidium. And from a theorist perspective, there are interesting opportunities if one uses different atoms. So, and since Jeff is working with a different atom, maybe he can comment on that.
Sure, we've got like 20 minutes for me to talk now about ytterbium. So in my group we use ytterbium for the uninitiated in atomic physics. This is an alkaline earth like atom, which means it has 2 valence electrons. It's like helium instead of 1, which is what rubidium has. And so it's a little more complicated, but we sort of have been operating on the thesis for the last few years that that this complexity gives you additional features without too much additional pain. And in short, those features are one, that you can actually encode the qubit in a nuclear spin instead of an electronic spin. So you have basically a pure nuclear spin qubit. It's very insensitive to both magnetic field noise and noise from the trap. So we have T2 star without dynamical decoupling at the second scale. The second is that it seems like we have a somewhat like we're on a good path to get to, let's say, very high gate fidelities. Manuel Endres in Strontium, which without having a qubit per se, but just entangling the ground in the Rydberg state, has shown it bell pair fidelities in excess of 99.8%. And we're sort of optimistic that by taking advantage of the same level structure and the same single photon transition, we can translate those results to a terbium. And then the third thing is things like, we are kind of the approach we're working on now is encoding the qubit not in the ground state, but in the metastable state, where leakage errors out of that state, which fundamentally should be the dominant errors from all of your gate operations and idling, can be detected by looking at the ground state atoms. And this converts leakage, which is otherwise probably your worst error and the hardest one to deal with, into an erasure when you know where it is, which is then the best error, the easiest one to deal with, that you have sort of double the code distance. And we've demonstrated in principle that this works in RB sequences with both 1 and 2 qubit gates. And now, extending that to the logical level, I think creates exciting opportunities for thinking about, how you want to structure your computers and your architecture, and whether you do gates online or offline and things like that. But I agree with Dolev's fundamental point that, many of the while there's important and fundamental differences that I think are going to matter a lot in the long run between these atomic species, a lot of the innovations that different researchers have working in different platforms can be, pilfered in some form and put together in some sort of super setup.
Great. Let me ask if there are any questions from the audience. Maybe while we are waiting for that, Misha, can I ask you a question? So this has to do with the whole thing about academia versus industry in terms of implementing quantum processors. So, we had sort of assumed a little while ago that, the amount of effort that goes into building a quantum computer is so large that it would have to be done in industry. And what's your perspective on it now, in terms of how this interaction should go and where should this sit?
So, yeah, I kind of want to maybe return to something that I said, is that, I hope this recent work makes it kind of very clear that, for example, this quantum error correction, this logical qubits, and, fault tolerance is not just an exciting engineering frontier, but also scientific frontier. So, and it's absolutely clear that we need to do hardcore engineering, but it is also very clear that, some, scientific ideas could greatly accelerate the path towards really kind of useful, practical quantum devices. And in that spirit, I really think that, we should create kind of a conditions such that, the leading university group and kind of leading industry players are really working together. And, this work that Dolev has spoke about, it has been indeed, done by a small group of grad students and postdocs. But we, hugely benefit, for example, from collaborating with our startup company, with Computing, which in particular help us develop some of the kind of hardware models, which eventually were integrated in our setup. And, we really hope that it sets kind of an example of how things should be done in future, so that's a
yeah, that's great. Thank you. Yeah. Let's see. Actually, while we are again still waiting for see if there are any other questions. There was a paper posted this morning by the group from IBM and possibly IMQ about classical simulation of your IQP experiment. So do you have any?
I would love to comment. Can I comment?
Maybe start, Dolev. Let me give just, let me start and
okay.
Okay, so first off, I want to comment that I actually think, so the issue is, can you use this kind of logical circuit to achieve quantum advantage? And actually, we were very careful in our paper to kind of steer away from this kind of claiming that we can achieve quantum advantage. So, so we implemented circuits which are hard to directly simulate classically, but we structured our circuit in a very special way, such that one actually, can have a reasonably efficient classical algorithm to actually simulate at least systems up to this 48 logical qubits. And kind of going into the details. So generally, this kind of circuits, the simulation scale to the 2 to the power n. So I think with our hack, we were able to reduce this time to the power of 2 to the n over 2 for the for this specific structured circuit, which we were able to kind of simulate. So, and actually today in the morning there was a paper from collaboration of IBM and INQ, which actually developed even a better algorithm, which scales 2 to the n over 3. So they used some kind of symmetry property. It's actually very clever, very cool kind of approach. But at the same time, we know that, for example, like, to beat, in our case, if we want to, for example, like convert our scaling 2 to the power n over 2 to the 2 to the power of n, we just need to do basically an extra layer of the gate. Likewise, to sort of circumvent this, this hack, which our colleagues have developed, all you need to do is to actually kind of, intersperse the circuit we have done with just moving atoms, with an extra step of moving atoms around it, so-called permutation gate. Maybe Dolev can actually explain it in more details. But actually what I want to really say, what I really find is actually very cool that here we're in the beginning of 2024, and we're actually talking about quantum advantage experiments with logical qubits. I think it's a very special moment. So, and I wonder, whether, John would think that it's officially an end of NISQ era, or at least a kind of a transition point. But maybe Dolev can answer in more details,
So yeah, maybe I'll quickly, so I agree with everything Misha said. I'll just quickly show a slide summarizing, if that's okay. Is that okay? I just have a backup slide for my talk in case it came up during the talk. You see the screen, right? So in this work, so it's not a quantum advantage experiment. These are sampling experiments, and we intentionally structured them in this way such that there's efficient bipartition. And this allows us to do this efficient tensor contraction that has this 2 to the n over 2 cost. And this attack on our, we again did this so that we could simulate it, but then and it's broken by applying additional CNOT layers. There's also this nice symmetry here using these minimal covering sets or minimal vertex covers of the CCZs that leads to like a 2 to the n over 3 attack for the exact circuit that we implemented. And this is broken by implementing permutation CNOTs within the logical blocks. Which is a nice, observation that if we're going to do a quantum advantage experiment, would clearly be important to integrate, because then and now, again, just by simply moving the qubits around each other, which is, directly attainable with everything that we do, we recover again at 2 to the n scaling. But it's possible that for the exact circuit we study, maybe there's another attack. So it'd be kind of nice to keep understanding that, and then we can come back at it and then, do like an actual quantum advantage test once we understand what all the attacks are and what the theoretical landscapes are. And also, I'll add one more thing on top of what Misha said, which is that something we only barely explored here, I think is very scientifically interesting, is, for example, we discard data, we do error detection, and this slows the measurement down, but it improves the score. That's also a pretty scientifically interesting question. Do you win or lose by you improve the score, you spend more time doing it, but then this actually, you can cross maybe a phase transition in terms of whether it's easy or hard to simulate. We should also be considering noise simulation. So I think there's lots of super interesting scientific things to explore here for sure. Yeah, that's the end of my comments.
But this transversal permutation gate, which I think is illustrated in this lower right side. So this is actually an example of this kind of gate with motion, which is, for us, basically like highest fidelity. It takes time, okay, but highest fidelity and basically kind of zero cost, which all of a sudden enables this kind of feature, which otherwise would not be present, right? So that's an example where this atom motion really adds a new, kind of completely new side to this story.
Thanks, yeah. I think David DiVincenzo had a question. Do you want to unmute and speak, David?
Sure, but I think at this hour, I only want to forward my question if actually somebody has a good answer to it, because otherwise we can leave this and think about it in the coming year or 10. But you see my question, you know, we've used at atomic physics instruments to look for changes of the fine structure constant, and we haven't seen any, but suppose it does change, will it break your Rydberg processor?
Of the fine structure constant in particular?
Yeah.
Oh, so no, not to my knowledge. I mean, because what we're doing in these hyperfine transitions is quite robust to that. I mean, okay, people with clocks are doing exceptionally interesting fundamental physics. Also, you know, not only clocks, but I mean, clocks in particular. And the tools we're developing here we're developing tools about, we have all of these qubits there and we're thinking about how to manipulate them. I mean, that, even if it's not in quantum error correction, because it makes you robust to everything, in our explorations of that, I think we should absolutely be applying that to fundamental physics. Yeah. But I don't know if this in particular will kind of ever be limited by something like, you know, dark matter. Yeah.
I mean, so basically, I think maybe one could kind of flip it to ask kind of in a more positive way. Can one actually utilize these techniques to probe, for example, this time variation, right? And so in principle, the systems like, you know, that Jeff is working on, and also Adam Kaufman and Manuel Andres, they, you know, that ytterbium, strontium, other systems which can be built for clocks, which have been proposed as a tool to measure this, you know, fundamental structure, constant variation. Of course, one might ask, you know, can this kind of error correction techniques can be useful to improve metrology? And this is not obvious, right? Because if you really do a full-blown error correction, you basically make yourself immune to all of these kind of perturbations. But, you know, if you have certain error channels, and I think, for example, I don't know if Jeff was part of this work, but, you know, people explored if, like if erasure, you know, conversion can be useful for clocks. And I think the answer is tentative, you know, tentatively, yes. And, you know, and I think like there is kind of, it dovetails to what Dolev said. It is quite likely that if one starts to use these techniques, which, you know, are being developed for this precision kind of metrology, you know, they would not maybe straightforwardly translate to improvement, but maybe with some creativity, there might be new pathways, you know, open to address these kind of questions.
Okay.
There's a question by Andrew. Maybe we can make that the last question from the audience. Andrew, do you want to unmute yourself?
Sure. Can you hear me?
Yes.
So my question's about the photonic interconnects that you talked about. You know, as we heard from John Preskel, you know, maybe we're in the age of movement for quantum computing, and we heard John Martinez express that, you know, we have a need for speed. I jokingly put in our kind of local chat, you know, wouldn't it be great if we had a quantum information carrier that moved at the speed of light? And I'm sure the photonics people are jumping up and down saying, ooh, 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 you know, but regardless of that, you know, there is this, you know, perceived notion in many quantum information technologies that there'll be a need when we go to large scale to have some kind of something like a photonic interconnect to put the pieces together. And, you know, you talked about how maybe you get to 10K. Misha said maybe there's ways to even get beyond that. But, you know, if we are going to try to get to these systems of practical quantum advantage, probably we're going to need something like these photonic interconnects. And I was wondering what your thoughts were about the degree to which that could become ultimately the bottleneck in getting us to the promised land of practical quantum advantage.
So I'll answer it. So okay, fantastic. So okay, so I mean, I'm split, I would be honest. So in the sense of like, there's the modules mentality, that it's the only scalable way because you have like a constant number of inputs and outputs to this thing, and now you can stitch them together. That being said, we have so many atoms and they all need to do the exact same thing. Maybe we can be very clever. So where exactly this trade-off will be of like, oh, at this point it needs to be photonic, I think unclear. So I think like, I mean, 10,000 is clear. Whether it can be pushed much beyond that, I think is very exciting research. There are lots of approaches people are considering to do these photonic interconnects. And I think in the coming years, people will probably do successful experiments, like really actually doing that. Jeff had a nice recent paper. There's also nice papers from Mark's group, Mark Safman. I mean, there's lots of, people are exploring that, and there's lots of approaches that are being taken, in particular here, the Harvard MIT community, and like things spearheaded, like, also from like Vladan Vuletic's group. So, people are exploring that, and I think in the next few years, it'll be clear that the building blocks work. There's clearly the building blocks are clearly possible. And then it will be a question of like, okay, in practice, do we want to do that? Because that sounds like a lot of effort too. So, that will be that, yeah. So I think in the next few years, the building blocks will be developed. Beyond that, then it'll be really practical, pragmatic questions of like, do you want to have all these things? What's the easiest way to have them, etc.
Yeah, maybe just two kind of like, I agree completely, but, maybe there are two asterisks or two additional comments I would like to make is that, like what, all of these things which we are doing now as a community really hugely benefit from is this kind of, optical multiplexing, this high degree of parallelism. And so our present thinking is to make these optical interconnects really truly useful. We should learn how to do these things in parallel. Maybe not at 10,000 channel scales, but, maybe at 100 channel scales, right? That's kind of one consideration. And the second, it actually, there is new theoretical work and new theoretical insights showing that, this, problem of optical interconnects becomes much more sort of, feasible, practical, provided this parallelism multiplexing can be solved if you actually operate with large blocks. That is, if you start working with systems which are already protected, which have already, where information is stored at logical levels, maybe, hundreds of thousands of qubits, physical qubits per block, connecting this type of things, is much more efficient as opposed to when you connect, few qubits, few qubit registers.
Yeah, I guess implicit in my question is just a concern I have about the difficulty of this transduction problem, that you have to mitigate, that you can work really hard and make a really great neutral atom processor. And then when you come to the point where you're like, okay, let's do something exciting, you're like, oh, nuts, I have to deal with this problem of getting it from one to another. And this is a whole new challenge that I didn't even think about.
But transduction is natural. And so maybe, I don't know, maybe Jeff or Dolev, you guys can. It's actually because we have an optical readout, so we have very natural coupling to light, right? We just need to collect sufficiently, right? Just.
Yeah, and I was going to further acknowledge that actually, in fact, like a lot of atomic physicists love putting cavities inside of their atomic physics experiments for many reasons. And so that is, I think, and that is, coherent atom photon coupling that people have developed. So that's one route. Another route is heralding. And there's like a lot of parallelism that you can do by heralding on, many attempts on atoms, that maybe each attempt has a low success probability. But because there's so many atoms and they're just all doing the exact same operation, it can also be parallelized. So I agree that we need to do it though. Yeah, but I think it's definitely theoretically possible for sure.
Great.
Thank you.
Well, yeah, thanks. So maybe we can do, if there's just a few minutes for final comments from the panelists, if there are any. Yes, please, John.
I noticed in our Zoom audience, we have Peter Shor, Dorit Taharonov, Michael Benor. So, I'm reminded, Peter proposed quantum error correcting codes in 1995, almost 30 years. And at last, we are entering the era of fault-tolerant quantum information processing. So it really is an exciting time. But we're still early days in fault tolerance. I think we have reason to believe, from what we heard today, that the Rydberg platforms will lead the progress in fault tolerant processing for a while. In the long run, I don't know. I very much agree with something that Misha said, that of course we need to face big engineering challenges, but this is really a scientific frontier as well, and the advances in technology will be really important, but ideas are really important too, and that's can propel progress in important ways.
Sorry, nobody asked me a question, right? My internet is just started to jump. Okay, sounds good.
Just final wrap up. So anybody have any comments, including you? If not, thanks, Dolev, for a wonderful talk, and thank you, Barbara, Jeff, John, Misha. Great comments, and of course we had as John said, we had a fabulous audience with Peter, Dorit, John Martinez, Michael Benor, lots of others. So yeah, thank you everybody, and see you in a couple of weeks.
Thank you, Mesh.
Thank you all. Thanks, Dolev.
Thank you.